And my dear friends, to the 8th Annual ACM Compute 2015 on Big Data and Analytics. For this tutorial session 5, we are fortunate enough to have Dr. Ashish Verma from IBM Amagas today. He has done his master's from IISc Bangalore in Electronics and Communications. He has done his PhD from IIT Delhi in Signal Processing. He is with IBM Research since 1998 and working in the area of machine learning and artificial intelligence. He is currently heading Smarter Planets efforts at IRL. Now, I request Dr. Verma to deliver a session on renewable energy integration.
Good morning, everybody, faculty members and dear friends. I'll be talking about the renewable energy prediction and integration. First of all, thanks for the nice introduction. So before I start, I'd just like to know my audience. So how many people have some background in semiconductor electronics? Can they raise their hand? Okay. And how many people know about data analytics and modeling? Okay, thank you. So I'd just like to start with an acknowledgement of my colleagues in IBM, the whole team who's working in the renewable energy area, and also some other faculty members and people at other industries, as I have taken some pictures or some comments from their presentations at slideshare.com and anybody else via mail. So here's the outline of my talk. I'll give you an overview of what are the different renewable energy sources and how their adoption is increasing day by day, and what is their importance. Just give a landscape to you in terms of the renewable energy area. Then I'll go a little bit deeper into the solar energy and the wind energy resources. What are the characteristics? What are they made of? How do they function, and so on. And then I'll be going into a little bit about what are the issues, what are the challenges when we want to use these resources. So for example, their unpredictability, their variability, and when we want to integrate into the grid, then what kind of issues we have to address. And I will have some concluding remarks. So I just want to say that feel free to ask questions any point in time. Don't wait till the end of the talk. If you have any questions, just stop me and go ahead. I'll be very happy if the session is interactive rather than one-on-one. So what are the renewable energy sources, right? So as you know, here's the definition from Wikipedia. So the renewable energy is defined as energy that comes from resources which are naturally replenished, right? We don't have to do anything. They are naturally replenished and at a human time scale. So it should not be that the replenishing is happening after 100 years or 200 years. No, it has to be a different time scale. And the examples you know very well are sunlight, wind, rain, tides, waves, and so on, right? And also geothermal heat. So all of these are examples of renewable energy sources, and they can be used to replace the traditional sources of fossil fuels like the coal, right, natural gas, and so on, or the diesel. For example. On the bottom, you see a trend. This is a chart from one of the reports by Bloomberg, and how the adoption is going to grow from the current situation all the way up to 2040. Right? We can see currently the mix is where 65% of the energy worldwide is coming from fossil fuels. Right? But if you look at 2040, it's the percentage is going to reduce to 36%. Why? Because all the additional or incremental energy sources are going to be coming from the renewable sources like solar and wind. So it shows a huge adoption which is happening in this industry because of many reasons which I will talk about in this section. So why we should use renewable energy sources, right? So what are the benefits? So first of all, they are abundant in quantity, right? You can use as much as you want. There is no doubt of that. They are free. There is nothing to be paid to anybody. They are natural resources. Of course, there will be some equipment cost which you have to incur when we harvest the energy, but there is no charge, no fee for them at the source. And they're clean. The biggest point, right? If you look at what is the biggest problem of dairy today, right? Because of the air pollution. We know that it's so harmful from a health point of view, especially for young children and for adults, right? The air is so much polluted. It is equivalent to like smoking a few cigarettes a day. Right? It's as bad as that. So, what are these are the sources of food? They are going to clean the air, right? They are very, very useful and they're very important point. What is about the challenges? One is because the technology is still evolving. So some of the equipment, whether it is solar cell or whether it is wind turbine or the farms which we set up, are high investment projects. So the capex is very high. Capex is the amount that you can buy the equipment. Right? So the capex is very high. You have to put a lot of upfront investment to basically install solar panels and wind turbines. So that is one challenge. The other one is as opposed to the traditional sources, like you can have a coal-based plant and you can very well control like, how much energy you want to. You can just do the knob and you can generate that much energy at that point in time. But that is not the case with these resources because these are controlled by nature. So how much sunshine will be there on a given day? What will be the intensity? How the clouds will go? It's not in our control, right? So that is the hard part. How do we address the variability and how do we predict and how much energy we can generate? So that is the hard part which we will address as we go on. This is just a worldwide view of which part of the world are generating how much clean energy, and you can see that we are actually quite we are not very advanced as far as India is concerned. Europe is actually has done a pretty good job in terms of the renewable energy generation and some other countries, but I think we are on a very good path. There are some more statistics on how different countries are adopting the renewable energy sources. So as I mentioned about the economics, right, and how the capex or upfront cost is a prohibiting factor to adopt these renewable energy sources. But what is happening over the years, if you look at the chart on the left, this is showing the cost for the solar panels. So how much you have to spend to get 1 megawatt of solar panel plant in place, right? The cost has been coming down very, very steadily, and the line here actually shows when it will reach the cost which is equivalent to the fossil fuels, right? And that is called grid parity. What is grid parity? Grid parity is that when you can get the solar energy or wind energy at the same cost at which you are buying electricity from your distributed or from your grid. So when it reaches that cost, it is called grid time. So it is very close to that. And of course, it depends upon the size of the plant, because if you are installing larger solar plants like hundreds of megawatts, 50 megawatts, then that will be much cost effective as compared to the rooftop solar panel which you can put on your roof, and that will be more cost. So, but overall the costs are coming down. And here is a more broader picture which is showing what are the cost trend for different renewable energy sources. So, for example, on the left you have most of the conventional sources which are like natural gas or coal and so on, and you can see the cost of those are. But in case of renewable energy sources, whether it is wind turbines, whether it is solar panels, or biomass, or so the trends are very favorable to us, so that we can use more and more clean energy as compared to fossil fuels. So we talked about the technology. I talked about the cost. Now, what about what is the other factors which are important here? So the other factors that are important is the policy, the government incentives, right? That what kind of incentives or what kind of policy the government is making to promote clean energy. So here is a picture of how many countries are actually adopting the renewable energy policies, right? And you can see there is an exponential growth in terms of the number of countries who are forming policies or rules and regulations, so that more and more people go for renewable energy sources. So that is another good thing for us. Here is a more specific picture which shows that what kind of concrete policies, so whether there are penalties being imposed, whether there are financial incentives being in place to promote the policies. So as you move along the x-axis, more and more specific rules or laws are being enforced to these countries, and as opposed to countries on the left. So there are targets, for example, you would know that in India there are certain targets have been set by the government and adopted by the Ministry of Renewable Energy. I will talk about that. So this is about those targets. So one chart of India, right? Where are we in the renewable energy area? So if you look at the picture on the left, this is the current situation where 59% is coming from coal and 12% of the energy is coming from wind and solar, right? And here is a breakup of the 12%. So we have about 22 gigawatt of wind power which is being generated, and only 3 gigawatt of solar power which is being generated as of December 2014. So for those of you who are not very familiar, 1 megawatt is 1000 kilowatt, and kilowatt is the unit you pay to your electricity, right? So 1 unit is 2 so that is 1 kilowatt hour, and 1 megawatt hour is actually 1000 times that, and 1 gigawatt is 1000 megawatts. So this is the current breakup, and there is a good mix here. But look at the projection, or look at the targets. What is going to happen is that by 2022 we are committing for 100 gigawatt of solar energy, right? So from 3 gigawatt we are going up to 100 gigawatt, and there are already new companies. If you are reading newspaper, the new companies being launched and established companies getting into this space to set up very large solar plants, very large wind turbine plants, where we can get energy and inject into the grid. So out of the 100 gigawatt, 40 gigawatt is going to be rooftop solar. So rooftop solar is where the solar panels are put on the rooftop of a residential house or a commercial building or an institutional building. For example, this building, you can put a panel on the rooftop depending on the size you have, and you can generate energy. While 60 gigawatt is with a large grid connected project where you can actually put these utility scale or very large scale solar plant and you can inject energy into the grid by having long-term budget agreements with the government. And similarly for wind energy, we have a very high target of 60 gigawatt. So as I mentioned, there is participation by various domestic and international players. Okay. So what are the different aspects of solar energy generation, right? What are the different aspects of how much energy we will get out of the solar panels? So first of all, there are different technologies for building the solar cells. So three of them are listed here, like monocrystalline, polycrystalline, and phosphor. And they are there's a trade-off in terms of how much cost goes in to build those versus what the efficiency of them. So typically, the efficiency for these three will vary from 15 to 20% to 30%. Right? But there are technologies where you can go up to 40 to 45% of efficiency. What does an efficiency mean? Efficiency means that whatever energy you are getting from sun, how much of it you are able to convert in electrical energy. That is how the efficiency is defined. Okay. So the very first one is what is the quality or what is the technology of the cell, solar cell. And then there are things like shading and shadow. So if you have a solar panel and there is a shade on that, for example, if there is an electrical pole or there is a building nearby and the sun and the shade, the shade is being shaded by a neighboring building or so. So the output of the panel will go down. That is the shading and shadowing. And it also depends upon the temperature and wind condition. Because lower the temperature, higher will be the efficiency. And also, as wind flows, then it will keep the solar panels cool and the efficiency will be higher. And then, as you know, it's all related to solar. There are different ways in which you can install the solar panel. And I'll very quickly show you some examples. Where you can track the sun, so that as the sun moves from east to west, how do you track the sun so that your output does not get much and you can get maximum amount of energy out of the solar cell. So here are different types of solar cells. The very first one on the left is the monocrystalline cell, which is very high efficiency. And then you have polycrystalline, which is kind of a little lower, but it is much more reasonable in terms of cost. And then finally, it is thin film, where there is only a thin film of semiconductor is being put on the metal, and that is the thin film. So here is a description of how the solar cells work, right? So basically, for those who have a background in semiconductor, right, there are different types of semiconductors you can build by doping. We can have a P-type semiconductor and an N-type semiconductor. N-type semiconductor is basically low, highly with electrons, and P-type is deficient in electrons, right? And that is also called pull. You can say that is dominated by pull. So this boundary between P-type and N-type is called PN junction, and that's what you also study in diodes. You have read the PN junction diode, right? So diode is being used in almost every electronic device nowadays. So think of it as a broad or a very large diode with a very large surface area. What happens when the photons fall onto this cell? The electrons actually move from P-type to N-type, and then if there is a circuit around the cell, it actually flows through that and goes and gets absorbed in the P-type material, and that is how the current flows. So more light comes in, more electrons will move through, and more electricity you can generate. So that is the basic phenomena how a solar cell works. Now, here is a description of the current versus voltage. How the current and voltage vary for a solar cell. This is a very similar curve which you will have for a PN junction diode, when there will be a closed circuit current, which is the maximum current you can generate, which you will achieve when the circuit is closed. There is no load attached, short circuit across the diode, and that is the current you have, the maximum current. And the maximum voltage you can have when the circuit is completely open. There is no load or there is infinite amount of resistance between them. So that is the open circuit voltage. What happens as T1 increases the voltage, the current first remains flat and then at a given point actually drops. Right. and that is a red curve. And so how do you get the power? Power is simply a multiplication of voltage and current. Right? So the blue curve is actually showing you the power. Multiply voltage and current, and you will get the power. And there is a peak which you will achieve, where you can get a maximum power. So why this is important? It is important that if you want to harvest X amount of power from solar cell, then at what point you need to operate the solar cell? What point you need to operate the solar cell? At this point. You need to operate the solar cell at this point, so that you get the maximum power out of it. So here is the same curve, but you see multiple curves here, and the multiple curves are coming from different amount of irradiance, different amount of solar irradiance which you can get on the cell. So as you would know that depending upon the season, whether it is winter or whether it is summer, and also depending upon the location, for example, whether you are near to the North Pole or whether you are close to the equator, the amount of irradiance which you will get from the source from the sun will vary. What happens as you get more and more irradiance, this curve shifts up. So you will be able to draw more current and more power from the solar cell as you are able to get more irradiance from the sun. So this is how it varies as you get solar irradiance, and that is very important because you want to know whenever you want to put a solar plant, you want to know how much energy I can generate from this plant or how much energy I can use from this panel. So you want to have a good prediction of how much energy you can generate, and for that it's very important to know that for that location what is the solar irradiance and how does it vary with us. So I talk about a little bit more into detail how do we predict, how do we build models which we can use to predict the amount of energy which can be generated from the solar cell or a big solar panel. So this is a typical very high level picture of how things work. So we have the solar irradiance incident on the solar panel, and the electrical current gets generated, and we have a charge controller. Charge controller is basically an equipment which controls at which point of that IV curve the solar cell is being operated. Right? So you have that IV curve, and there is one point at which you can generate or you can draw maximum power. So this is the piece of equipment which actually determines that at what point I should operate the solar cell. So it goes to the charge controller. It actually determines the voltage which needs to be maintained across the solar cell to get the maximum power. And then it goes to a battery system for storage. And because the current which is being generated is a DC current, you need to put an inverter to get the AC power. So there are some equipments which you can run on DC power directly. For example, nowadays all the LEDs, even the DC fans or many other equipments which can run on DC. But if you want DC power, then there is an inverter which needs to be put before the supply. So this is a typical flow how we get power from the solar panel and then get the AC power, which is what we require. Okay. So now let's get a little bit deeper into this whole phenomenon of solar irradiance and how things work. So, so there are three concepts here. One is called DNI, which is direct normal irradiance. This is actually, if you would put a solar panel perpendicular to the solar rays, then that amount of irradiance will be called DNI, direct normal irradiance. Right? And then what happens that there will be a lot of objects around the panel. For example, there may be a cloud, or there may be a building, or there may be some other objects around the panel. So the sun rays will go hit that, and it will get reflected and then come to the panel. So all those kind of energy which is hitting the solar panel through other objects is called a diffuse horizontal irradiance. Diffuse horizontal irradiance, EHF. So the total amount of irradiance which you get on the solar panel is actually a combination of the direct irradiance and the diffuse irradiance. So it's basically a summation of DNI plus DHF. So that is used to determine how much solar irradiance we will get on the panel. And then to compute something which is called plane of array irradiance, which is basically how much irradiance you will get on the panel by using the solar irradiance and also angle of the solar panel. At what angle you have to put the solar panel. If, I don't know how many of you have seen solar panel, they will never be put flat. They will always be put at some angle. So that is actually the reason how what angle you are putting the solar panel so that you can get maximum amount of the radiance on it. And here is, as I mentioned, that you can actually have panels track sun, right? You can track sun so that typically what happens, you will have very low amount of radiance in the morning when the sun rises, and then it will slowly go up, and it will peak out around 2-3 p.m. and then it will go down, right? So what you can do, you can actually have a moving object beneath the solar panel so that it tracks the sun, and there are you can have it moving around 1 axis or 2 axis, and accordingly you can track the sun so that your variation in the day or even seasonal variation can be minimized, so that you get maximum amount of solar radiation and has maximum amount of power from the panel. By the way, please interrupt me if something is not clear to you or you want to ask any question.
So in this case, do we have some of these kinds of movable objects? Obviously, it will be cost.
Yeah, right.
So no, the question is like, in case in India, basically everything has been considered as quite good sunlight months. So will it wait for? It depends on the intensity of the light if you move.
So this will vary on a daily basis.
On the daily basis.
Based on based on the sun. Based on the sun location, it can actually adjust its inclination so that it is as close as possible to the perpendicular to the sun. So if you look at the daily variation, it will be 1 axis, but when it goes from summer to winter, the sun actually changes its trajectory, right? So then you have to go to the other axis also and move it accordingly.
Meters all by this.
Yeah. Of course, it will be very expensive. So we have to do the ROI. Whether that is the right and all that. What I am talking about is mostly from a technology point of view, right? What is available, what you can do. But there will be an ROI side of it also. You have to look at what is the cost. And that is a completely different topic because that will depend on who the vendor, right? What is the data period you are looking at, right? And so on. So, but this is available and it's not very rare to have at least 1 axis.
What is the minimum light intensity required for?
So the maximum you can get is 1000 watt per meter square, which is the benchmark. And then it can go down as low as 200 watt per meter square. So for example, in the night it will be 0, right? So or close to 0. So it varies in that.
How many hours of sunlight is required?
So typically, so there is nothing required. Basically, whatever sunlight you are getting, you will generate in that period, right? Typically, what happens like when the sun rises at 7 a.m. or 8 a.m., you will start producing very small amount of power, and then as you go towards 2 to 3 p.m., that is when you will peak out, and then again.
Can we store this?
You can store the energy if you have a storage. What I'm not talking about is storage, which is actually a very important aspect in all of this, right? Because if you look at solar power, it has a very definite pattern, and then you also have to look at what is your load pattern, right? So, for example, the load will be peaking at morning when people are leaving for office or they're getting up, getting ready, and all that, right? And then when they come back from their work, then again you will see a peak. So there will be a solar energy peak and there will be a load peak. How do you manage that? And that you can use using storage. But again, storage is very expensive. Nowadays, with that option of electric vehicles, that is it's like a revolution because you can use electric vehicles as a storage. So you can charge them when you are not using. So for example, you can just put it in the parking. They get charged by solar energy, and then when you go home, you can actually use it as a battery to supply power to your home. So they can be used as a moving storage for that is what we call peak energy or peak share. You can use that for peak share.
Generated power is DC or AC?
So solar power is generated is DC. and then it is the converter. So in fact, nowadays, so there is obviously a loss, right, when you convert DC to AC. So nowadays, there is a lot of focus. In fact, many people in India also working on completely DC grids. So if you can have a DC grid within your house, you can directly use the solar power without converting into AC and minimize the loss. So because a lot of devices nowadays, your LED, mobile phone chargers, laptop, everything is DC. So what we end up doing is we convert things to AC first, and then we again convert to DC, right? And use it for those devices. So there are initiatives where you can have either a complete DC or you can have a mixed mode. AC or DC for
What is the average setup cost if I go for 1 kilowatt?
That is something I don't remember offhand, but there are numbers available easily available for Indian conditions. It varies a lot.
So how do you looking for like such ample knowledge regarding solar energy? What is the time frame we can reach to grid parity?
So grid parity is, so for example, in US, right, the grid parity is already there. Already is
Through solar?
So grid parity, but remember grid parity I'm talking about, I'm not talking about rooftop solar. I'm talking about large scale, large commercial, because smaller plants will be more expensive, right? So, but if you talk about utilities, yes, solar is there already in grid parity. In India, it is still a bit more expensive, but as you see, the last 1 year, MP government, Gujarat government, and Tamil Nadu government, they have been able to sign PPAs anywhere from 5 to 7 rupees per unit, right? Which is almost like grid parity. Even Karnataka is in this bracket. So there is, it's already there. It's started happening.
If we set up this particular solar, what is the average lifespan?
Yeah, so average lifespan is 50 to 20 years. It can last up to 30 years. But efficiency decays. It will not be the same for all. And in fact, the maintenance is pretty low for solar as compared to wind, because mostly it is about dust. Wind is a much more costly affair.
Predictability will be an issue in case of grid.
Both. I'll talk about wind. Oh, yeah. So the next topic is good segue. So now let's go a little bit into. By the way, each of these topics are kind of a course on their own. I'm just trying to cover in 20 minutes, but there's lot of material, lot of very interesting and exciting stuff. If you want to go deep into how the solar cells work, how the model them, right? I just briefly touch upon each of these things so that you know, what are the different issues and you can go and follow and study this further. So, so the other prominent source is wind energy, right? So, if you look at a wind turbine, right? Wind turbine, what it is doing is basically converting the kinetic energy into thermal, right? And the capacity of the wind turbine can vary a lot. You can have a 100 kilowatt wind turbine, or you can have a 50 kilowatt. In fact, now there are companies who are building up to 5 and 7 megawatt of wind turbines, like daily. But 3 megawatt wind turbines are quite common. And the output depends upon the wind speed, the wind direction, and to some extent on temperature. Temperature also affects how much power you can draw from the wind turbine. And there is unlike solar. Solar is a pretty dumb device. You just put it there and keep on generating power. But wind is as I said, is a very complex affair, because what you have to do, you have to continuously adjust the blade positions and the directions of the wind turbine so that you can draw maximum power from it. Because wind, there is a velocity and there is speed and there is direction. Speed and velocity. Velocity varies all the time. So how do you make sure that you generate maximum amount of power from wind turbine? So how it is done is that there is something called pitch and yaw control. So pitch control is these blades of the wind turbine are actually movable. They can rotate like this. They can rotate the blades depending upon what is the wind speed and what is the wind turbine. And actually you can have to get in such a position that the wind will just pass through it, the turbine will not be able to. So you want to curtail, you can actually do that. Yaw control is basically when you move how the wind turbine faces. You can actually move the whole plane of this turbine and try to draw the next column from it. On the left, I have a typical curve which is showing you the power versus wind speed of a wind turbine. And this kind of curve you will get from a manufacturer or the supplier of a wind turbine. So what happens in the beginning when the wind speed is very low, you basically don't generate any power, right? And when it comes in the 2 to 3 meter per second range, you can start generating power, and then you go all the way up to a certain speed. But when you hit maximum speed, which is set up by the manufacturer, you actually stop at that. You don't let the wind turbine run beyond that speed because the wind turbine may get damaged. But there is a very sophisticated machinery behind the wind turbine, which actually has all the gearboxes, all the inverters, right? It's a huge. This part in the center is called nacelle. It is actually very big. So it's like a big hall, right? Big hall, a big room where all these equipment are there. You want to make sure that you actually give at a certain wind speed beyond which you don't let it go further. So that is the curve which shows the wind speed versus the power you can generate. And here is an actual data point, right? So you can see all these blue points which are actually showing that what are the because that is the more theoretical kind of curve. This is the more practical curve where you see that how the power is generated for different disciplines. Because it actually varies. It's one of these numbers. It actually varies depending upon the practical principles. So this is the picture of a single wind turbine, right? Now what you do, you go for a wind farm where you have multiple wind turbines. So what happens? Unlike solar, basically in solar you can put as many plants as you want, right? And there is pretty much no interaction between the solar panels. So between one solar panel and another solar panel, there is not much interaction. You just generate independently power and you can combine them in series of parallel components. But here, when you are putting a wind farm, then what happens? There is some interaction between the wind turbines, and that is called wake. What happens, as you see in this picture, when the wind passes through a wind turbine and the wind turbine is rotating, there is a turbulence which is created in the wind, and you can see how big it can. So the wind turbine which is here, what happens? The wind speed which this turbine is able to get, this turbine is not able to get exactly. The effective wind speed reduces, and plus there is a lot of turbulence for the wind turbines to shut down. So that is called wake. So when we are looking at a wind farm output, it's not only important to look at the wind speed, wind direction, and temperature, but also the wake. So there is a modeling which is done that how to model this wake, and there are different models using data-driven models and there are physical models. So basically, we compute how much wind will be the wind speed at thousand turbines. And as it is said here, it can actually go up to 20% less wind speed as compared to the front. So as I mentioned that in wind, in the case of wind, you have to do much more work than solar to optimize the amount of power you can generate from the wind. So what you have the farm layout, you have the wind parameters, and you have the meteorological data. Meteorological data is basically the weather output. What's the weather forecast? Weather forecast will give you that how much will be the amount of average wind speed and direction for that particular region. So you can use that information along with the pitch and yaw control and the torque control. Torque control is basically that when you want to the limits which I showed in the last class, that at what point you don't want to turbine to rotate beyond that speed. So you can use different kind of control and the wake model to maximize the amount of energy you can get. there is an optimization model which actually takes all these parameters and determines what is the optimal grade position and what is the optimal yaw position of the wind turbine. How it should stay and what should be the position of the blade so that we can protect maximum amount of power. Why this is important? It is very important because for a large wind farm, when we have, let's say, 20 turbines or 50 turbines, even 1% can improve the yield by 1%. It can be millions of dollars. So it's very important that how do we model the wind farm, the interaction between different wind turbines, and how do we optimize so that we can get the maximum. So that is how the wind turbines work. And in fact, so far, even in India, the wind energy is dominant as compared to solar, and mostly because of the cost. But now the solar panels have the cost coming down. Solar is predicted to surpass that range, and solar is going to overtake then the that. Okay, so now I will get into a little bit of how do we look at the variability, how do we study that, how do we model the variability, and how do we predict the variability coming from this source. So here is a typical, if you want to look at the end-to-end system, how we model things, how we study things, right? Renewable techniques. So as you know, for both solar and wind, weather forecast is very important. You want to know first now how much will be the solar irradiance coming in the picture, how much will be the wind speed, how much will be the temperature, rainfall. All these things are very important for both solar and wind energy and solar. So we have the weather forecast model, which is actually an input to the renewable power forecasting both for wind and solar. And then we also have a load forecasting piece, which actually looks at what will be the load at a given point in time. Load or demand, whatever you want to call it. It's basically looking at how much people will be consuming or requiring at a given point in time. And both of these are used to basically come up with a forecasting engine that how much energy we need to inject into the grid, and that also determines the price of it. Right? Because as you know, there is another aspect how the utilities purchase power, and actually the price can vary at real time. So a lot of it can also feed into how the pricing works and how it will fit for energy. So this is a complete picture in terms of the renewable energy prediction and integration. Now let's go a little bit into each of them. So when you talk about forecasting, right, if you want to forecast the renewable energy, what are the different methods? So one set of methods are physical methods. Physical methods are, for example, when we model the solar panel, we actually model the like PV IV curve threshold, that how much current will be generated, what is it, how it will have a complete solar model and a PV model, and the I think that from the forecasting. The other set of methods are data-driven methods. So you don't worry too much about the physical body. For example, in this experiment, you have to have that how the wind turbines are located and what is the specification of each turbine and how the wind is going to pass between these turbines. You don't have to worry about that. What you have to know, you have to look at input wind speed, wind direction, and temperature, and maybe just the coordinates of the wind turbines. You take all that data and look at the historical data for energy, how much power was generated at a given point in time, and then make a statistical model from the source. These are the two different approaches. And of course, you can combine these two models so that you can get better models than either one of them. And there are various rule-based methods or machine learning-based methods where you can combine multiple models to come up with better. Okay. So just to reinforce what I said, how do we use the power forecasting? Actually, we have a weather forecast. So from the weather forecast, we can get the GHI, which is the global horizontal irradiance. We look at the ambient temperature, and then we have the parameters of the solar panel. For example, the location and orientation of the panel, and the historical data that for the last 1 year, for last 5 years, how much energy was generated by those panels and what was it. And using these two, you can actually generate a model which will forecast the irradiation on the panel. That model can be used for here is a picture of a real system from ACM, which actually is a complete stack, which starts from different forecasts. You can have multiple weather forecasts. For example, the forecast which is given by US agency, NOAA, NOAA, for the whole globe. Then you can have a forecast localized for that, and you can have different models predicting predicting the forecast. So you can have different weather forecasts, and then you can convert them to solar irradiance again by using different models, like radiation transfer. And on top of that, you do a model blend. Blending is actually when you mix multiple models to generate, to improve the accuracy and stability of these models. So this piece is doing the blending part, which is the core of it, and it uses the machine learning and the data, historical data, to basically come up with a model. What it does, it actually looks at that which model is doing better at what conditions, by what conditions. So some model will be doing better for a certain weather conditions as compared to other. So it learns using historical data that how much weight I should be giving each of the models depending upon the historical data, and then find out the optimal way to combine these models. So this is and this actually improves the accuracy very high as compared to the traditional models which use just one model to predict the forecast. So there is an output of the model, of the blended model. So you can see some black dots are actually the real data points, and the curves are the curve is the forecasted data. So you can see that it's pretty highly accurate. Of course, some of the points it is not able to capture, but most of the time it is able to capture. And there are different metrics like root mean square, mean percentage error, or mean absolute error. We use different metrics to measure the accuracy. Not only do that, but the accuracy can vary from 20%. But the error can vary from 20% to 5%. The accuracy can vary from 80% to 90%, depending upon.
So who's doing it? Is the company like IBM is doing it or government company?
IBM is doing it.
IBM is doing it.
There are many.
It's quite complex.
Yeah. So there are many entities who are doing it. IBM is one of them. But there are companies, US government of course is doing it.
So they are doing it for their own money, the government has asked them to do what they pay because they pay.
No, so what happens that whenever you are setting up a very large plant, the government mandates you to give a forecast of how much power you will be generating at an hourly level. And so the forecasting can be done either by the vendor itself who is giving by the plant, or it can be done by a third party, for example, any company. So government does not do it for them, but government mandates them. But there are some research labs. For example, in US you have NREL, research laboratory. So there the research team actually does a lot of research on it. You can benchmark against them. That how do I compare this with their technologies? So in fact, for us, we are doing much better than.
So from where are you getting this country data? Or IBM is maintaining its own?
So what you can do, whenever you install a solar plant, right, you actually can measure how much energy is being generated from the panel every minute. So you can get that data. And there are equipments. Maybe I remove that. There are equipments which actually measure the irradiance, solar irradiance. You can measure both of these things, let's say for 6 months or a year. And then you can use that data to then.
You can month data to go for good for forecasting.
So if you look at weather, right? So there are seasonality just like some different seasons. So you could have at least 1 year of data. And that also depends upon the forecast could be for next half an hour or for next few hours or for next a day ahead forecast, or it could be for let's say 10 days. So depending upon the time scale of the forecast, you need to use different times and different data. So for example, if it is let's say there are various techniques which are used. One technique is where you just look at your camera, you look at the sky. It's called a sky-based sky camera. So you look at the clouds, how the clouds are moving, and you predict that let's say next 10 minutes, next 30 minutes, how the clouds will move, what will be its effect on my solar panel. And that is being used to forecast for a very near term. Now, there is another technique which uses satellite data to again capture the clouds, but then you can cover a much larger space. And you can capture a lot more clouds in a lot more, lot bigger region, and then you can do up to let's say a couple of hours. But if you want to do anything beyond let's say few hours, beyond 6 hours, 8 hours, then you have to have a proper weather forecast. So you have to have a weather forecast, and then you can use that to come up with the estimates.
Steam computing. Sorry? Will it comes under steam computing?
Steam computing.
Yeah.
Yeah, so for the very short term models,
you want to move so that some of us ask how this value from that. How do you think like things are local land or like this data is better or not?
yeah, good. So the very first one is let me just go back to this chart. Yeah, if you look at this one, weather forecast model, so there you actually need a proper because if you want to do a large region, because there is a lot of data which need to process. For example, we are using blue jeans. We are using blue jeans as a supercomputer, and in a general term, basically we have a constant to do weather model. Or you can use a weather forecast which is being supplied by the government. In this case, it could be IMD or in government, US government, anyway has free forecast.
IMD is not maintaining regularly written. I tried from IMD and it's
very hard
data from 2008 or 2009.
Yeah.
Not
So
India data.
yeah, there are some challenges in India. But if you want to do your own, you can do that too, but not have a very good amount of compute. As far as the once you have the forecast, the compute wind and solar forecast, you don't need a huge amount of compute. You can actually use a machine learning based method. If you have data, let's say for last 1 month or 1 year, you can actually train machine learning based models. And you can do it. There are many IBM products also available like ABES, but you can use other products also. And that can be done on normal server also. So that is one. And load forecasting again can be done on a quite normal machine. Anyway, when you do a lot, you are doing a very large spatial temporal model. There you need because it is dominant in this time. There is a lot of partial involved and a lot of points involved. That is very important. There is a tool by the way called Renewable, which is yes from earlier. You use that tool that is very helpful to do a lot of steady state analysis. But if you want real time forecast, or you want to translate a logical okay, so let me go back. Yeah. So I talked about the solar forecasting system. Here is example wind forecasting system. I just speed up getting the time. So what happens in the wind forecasting system? This is again a system, complete system which looks at that there is data coming from, for example, SCADA data, which is coming from various systems placed in there. There is public data which is coming, for example, weather forecast or terrain data, or you have a lot of these data which is about the terrain, like what is surface, what is the roughness of the surface, what are the different, whether there are buildings nearby, whether there is forest, what is the landscape, that data, and that goes into the whole modeling. Again, we look at the weather forecast and the turbine power forecast, and then from the turbine power forecast, you go to the farm level power forecast, and then you measure the performance. That how good I am doing on the project. And on top of that, you can have UIs where you can actually real-time monitor that how much wind power I am getting, or as a forecast. Here is an example. You can see this is actually this is real data coming from very large firm in US. What is so the green curve is actually the measured power, which is actually the real observed power, and the blue one is the forecast power. So you can see that it's following the trend, but at many places it is going off. Right? So here again the accuracy is in 80 to 90% range, and basically this is used to get a sense of how much energy they want to use from the traditional sources and how much they are going to get from the renewable energy sources. Okay. Now let's go to the final section of the talk, which is where I will talk about what are the different ways in which we inject renewable energy into the grid and how to challenge. So there are various deployment models for these renewable energy sources. For example, I already talked about utility scale, which are very large solar farms and wind farms. Then you can have medium scale implementation. For example, you want to do it for a whole campus. Let's say this campus. For this campus, you can have a renewable energy plant which you can install. Or it can be for nowadays these private builders, right? For apartment, a large apartment, they can have solar plants, or they can even plant. There is also a new trend which is starting, which is called solar parks. So solar parks is a phenomenon where you don't have to put a rooftop solar on your roof. You can rent a solar panel in a park. There is a third party will actually put a lot of solar panels in a common place, and you can actually rent that and get the benefit. And then of course the small scale is residential rooftop or office buildings, and just for one building. And then of course nowadays a lot of these data centers, in fact, as you know, Google and Facebook, right? There is a lot of renewable energy for the data centers, like huge data centers running on renewable, which is a good thing for us. So there is another way to cut at it, that these renewable energy installations will be isolated, which means they are not connected to the grid. Whatever is being consumed, whatever is being generated, you can consume within the system. So, for example, if it is a home or it is a microgrid, so let's say there is a we have set up a microgrid, for example, in the rainforest, where all the power energy generated is consumed. Or it could be grid time. So grid time meaning that you consume whatever is available, and then rest you can inject it into the system. Or you can generate whatever you generate, you inject it into the system. That is different. So, for example, if you have a solar panel in your home, and I think the regulations already there in Delhi and in India, there are two modes. One is for a million tariff, where you can directly connect the solar panel to the grid and get paid for how much you inject into the grid. And there is another mode in which it is called net meters, which means that you will consume first in your home, and then whatever is surplus that will be generated into the grid, and your units will be offset against how much you are using. That is called net metering. You can actually think of it as a two-way meter. You measure the power flow in both directions. How much you are consuming and how much you are getting. Only the balance will be charged. There are two modes. So just like here is an example of the isolated grid, and then you have to look at what is the size, because we are using only, we are putting it only for one use, then what is the right size? It should not be very large, then you would be wasting energy or should not be very small whether you are going to develop your requirement. And you have to look at what is the amount of storage I can find so that you can run it in an optimal fashion. And the other mode is of course grid connected. So there is another term which I want to introduce, which is called distributed energy resources. You will hear about this term again and again. It's become very common. It means as opposed to the previous or the historical trend where energy was generated at one place at the generating station and it is transmitted on the loads. But now it is completely opposite. What is happening because of the renewables? There are energy generation has become distributed. So you can generate energy at your home, you can generate energy at a building, you can generate energy at a distribution center, and it will go in either direction wherever the nearest. These are called distributed energy resources. And then you have to look at different models as I talked about, within tariff, contract or even fixed term contracts. So whenever you have large installations, you don't look at within tariff or net metering. You go to the government and say, okay, this is my generation capacity, and every government actually can build, and those are some prices for they will be 10 years, 20 years of agreement where they will be supplying forward to the government. Okay, so we already talked about this, right? We are having a lot of variability in the energy space because of the weather, because of cloud. Aerosols are basically different particles which are present in the air, and when the sun rays pass through the atmosphere, they get impacted or they get absorbed due to the aerosol. That's very important to look at. In terms of water variability, so all of it essentially affect how much the radiance reaches the solar panel. And similarly for wind, we have wind speed direction and the wave length. So what are the challenges, right? So the challenges are that it goes here. So let's talk about the wind energy. So in this chart, what you see, this black curve is the load, how the load is varying, and the red curve is the wind energy, and how the wind energy is varying. Now, what happens when you, so how much energy, so whatever energy you want to, you are generating, you want to put it into the grid, and whatever you require as whatever you require more to supply from the traditional source, like your coal plant or your gas plant. So there is something called net load. So what is the net load? That you take the load, what is the requirement, and subtract the renewable energy which you are getting from these sources. So that is the net load, and you can see the variation of the net load here. This is load minus wind. So what is happening? As a result of injecting renewable energy, the net load variation has become much higher as compared to the original variation in the net. And as you know that if the load varies a lot, it's very difficult for you to basically supply power reliably. Because what it means that at some times you need a lot of power, lot of capacity, and sometimes you need very small capacity. So there are a lot of these ramp ups and ramp downs which are required. So ideally you want a flat load so that you can estimate how much energy you want to generate and just be done with it. But that's not the case. In fact, it is going in the other direction. That variability in the load is increasing because you are injecting renewable energy. So that is one of the biggest challenges. So whenever we inject high amount of renewable energy, these are the challenges which we face. One is the ramp up and ramp down requirement. So ramp up and ramp down is certainly, let's say your load is going from let's say 10 megawatt to 30 megawatt. So and within a few minutes, so you have to ramp up your generation in a very fast manner, so that you can meet the load requirement. And that is not easy. That can also mean that you have to have a lot of spinning so that you can fulfill the load in a very short time. And then your stability, and if you inject a lot of variability into the grid, what can happen? And as you would remember that 3 years ago we had a major grid breakdown, right? So and the result will be blackouts. So we have to be very, very careful about stability of the grid. So whenever we inject a very this kind of energy to the grid, there will be voltage and current fluctuation. and we have to make sure that they reach a steady state without these stabilizing. And finally, the redundancy requirement, it can also have implications on the redundancy. So if there is a failure in the generator, then this kind of variability can also require more redundancy to be generated. Okay, so I'll quickly go through this case study, and I know I'm standing with my time, so I'll finish next. So what we did in one of the isolated grades in the earlier unit, this is a grade which is isolated grade at 7 kV grade, and it is serving a load of 7 megawatt. And it is running completely on diesel engine. There are 4 diesel engines of 3 megawatt each, and they are basically what we wanted to do is to determine how much maximum solar we can integrate into the grid without destabilizing the grid. And here is a overall methodology how you can determine that how much energy you can inject into the grid. So we have the historical load, we do a load forecasting from the historical data, and then we basically run a loop where you look at that whether I am able to satisfy the ramp up condition. Remember I mentioned that you have to ramp up or ramp down whenever the solar energy goes up or goes down. So you have to look at that today you are going to use it all the time for all the steepest variation of load to the for the load and energy calculation. So that is called a steady state analysis. And then the next level is that even if we can meet the ramp up and ramp down requirements, whatever voltage and current fluctuations are introduced into the grid, can they be sustained? Can they be sustained? That is what transient analysis. Basically, we look at steady state and transient analysis. Transient analysis has 2 flavors. That one is just because there is cloud cover movement, how the energy is varying, and the other one is something goes wrong and the whole solar plant panel gets disconnected. Then what happens? And looking at all these scenarios, we want to determine that how much solar energy we can get. So I'll skip some charts. I'll directly go here. This is the steady state analysis. So what it is showing is that this is the load, x-axis is the load, and y-axis is the amount of generation capacity or amount of renewable energy you can have. So blue curve, let's look at the blue curve. What is the blue curve saying? The blue curve is saying that whatever is the amount of load, you need actually plus 4. You need actually plus 3. So if there is 1 megawatt of load, you need 4 megawatt of capacity. Why is that? Because remember I told you that there are 4 generators, 3 megawatt. So that is a redundancy requirement. So if any of the generators goes down, the rest of the generators should be able to serve them. So that is why it always has to be more than 3. So this is the normal capacity requirement. And the total capacity from the 4 generators is 12 megawatt. So we cannot go beyond this because we can only go up to 12 megawatt. So we cannot go beyond this region. So that means the total energy which we can have is 9 megawatt. And then what happens to the renewable energy? So for renewable energy, what we want to do is basically, first of all, diesel generators we need to look at that can be completely shut down the diesel generator or they have to be running. It turns out that we have to keep the diesel generators running because in case the solar goes down, they have to ramp down. So they have to be running at a minimum load, which is 1 megawatt. And beyond that, if we switch on the generator, then they cannot ramp down. So basically, we need 4 megawatt of generation coming from the diesel engine all the time. So that is why the renewable energy which can be integrated is always less than the total energy which can be. So by this analysis, you get that 9 megawatt of for 9 megawatt of load. For 9 megawatt of load, you can generate up to you can basically use up to 8 megawatt of solar energy. But that is currently the load there is about 4 megawatt. So so we can use up to 3 megawatt of solar. So that concept, to do first the stability analysis from a statistic point of view, to look at just cater the ramp up and ramp down, and the generation, what is the decision that taken, what is that, and some of the solar analysis. And then you go to the transient analysis. For transient analysis, there is a lot of complications which is done. And this one, several questions, yes, can be used to run the transient analysis, the load flow analysis. So there, the whole grid is modeled. Each line, each transmission line, each transformer, each equipment is modeled. And basically, you look at it, there are certain voltage and current fluctuations which are introduced, whether the grid can take them. Right? What is the result of that? Basically, it seems that, for example, if you introduce 6 megawatt of RAM, then what is the behavior? And if you use 7 megawatt of RAM, then what is it? We can see that at 7 megawatt, the grid becomes unstable. So that gives us limit for a transient analysis. And of course, we have to take least of that because we have to meet all the conditions. So in this case, we basically come to look at 6 megawatt. Just to show you how we get that, how we go about the renewable energy and how much it is, what is the behavior of it, right? So this is a sample data point which shows that this is the actual solar energy output for short term. Right? So this shows how much variable it can be. It can be really varying a lot, and we have to make sure that the grid can actually sustain this kind of thing. And we can get to the level and have some because of this huge amount of variability. And this is the chart which is showing the minimum amount of load if the diesel current is established. So, if, for example, what can happen that your solar is coming down and the load is going up. You have to look at the worst condition which can happen. So, what is the runoff is required? For the runoff will be even higher in that case. So, you have to cater for those conditions, and that is why the diesel generators have to run at least 1 megawatt to cater for this. Okay, so that is it. Just to conclude, what I mentioned that adoption of renewable energy is increasing a lot, and even in India, there is a lot of big plants and a lot of private players as well as government is taking a lot of initiatives to use the solar energy. And as we adopt this more and more, and as we get more and more of these deployments, it will be very important to forecast the energy in a very, very accurate manner. And how do we basically use it in an efficient manner? And so, as you know, that there's a high amount of variability in these resources, and there's already a lot of talks happening at the utility level, the distribution level. Can we actually use this amount of renewable energy? What will happen to the grid? And will the grid be stable? Will they reject this 100 kilowatt energy? So, this kind of analysis is very, very important, and you will see a lot of usage of it going forward. A lot of people will be working on it to actually make sure that we are able to suggest more and more. The last point, which I had no time to talk about, I had to chat, but I have no time to talk about, is the storage. The storage is one thing which can actually cater a lot of these variability. You can actually store in the surface, and you can store, and then you can have less energy to actually use. And it also is very good in ramp up and ramp down. But again, storage is very expensive. So, how do we optimize the use of storage, and how do we use the storage in such a manner that the battery life is maximized? All those are very, very important area of segregation. So, thanks a lot for your attention, and if there are any questions, I will be ready.
So just a hospitalization session, just quick payment. Someone asked, I have a 1,000 square feet house. Can I run it on renewable?
Yes, you can put up a solar plant. You can put a solar plant on the roof now, but it depends on what your consumption.
I do want first.
Yeah, so, right. So 5 kilowatt you cannot generate on 100,000 square feet. Right? Because maximum you can put like 500 watt Only 1 kilowatt. So either you use storage, right? So that because you will not be using 5 kilowatt all the time. For example, at night, you are using 5 kilowatt is probably the peak, right? So you can use storage to serve the peak, right? And you can store it when you are not using. So storage can help you, but probably 5 kilowatt will be difficult to completely, you cannot get complete from the solar panel. But partially you can.
Besides solar, any other energy for our house? That is the actual question.
See, wind is not visible from house. Mostly it is solar.
Then units per day usually the consumption to normal household.
Yeah, exactly. So, between 1 to 2 kilowatt, you can put now for a medium house with storage.
What is the scope of the grid energy in North India?
Yeah, so again, we have to look at the terrain, where there is good wind all the time, right? So in India, most of the southern states are good for the wind profile. Northern states don't have that much of good wind profile. So it all comes down to ROI, right? If you are putting a wind turbine, yeah, most of the wind turbines are there. All of it will depend upon how much water invest and how much you can afford the cable period. So, but relatively, southern states are there. In Maharashtra and Tamil Nadu, even in Uttar Pradesh, they are setting up.
But in Rajasthan also we have
Yeah.
in Jaisalmer side they have
So I don't think they have a big, but I have seen relative.
they don't have a very farm actually. They have just wind turbines kept in series kind of thing. And they use it for the purpose.
Yeah. So nobody is stopping to put wind turbine, right? You can put wind turbine, and in fact, you can do an analysis that how much energy you can generate from wind turbine over the year. There's data available.
Thank you so much, sir, for such an enriching and enlightening session. Now I will request Professor Yogesh Mittal to please come on stage and hand over the memento. Thank you, sir. Now I will request Mr. Ishan Verma please to come on stage. Thank you, sir. With this, we come to the end of this tutorial session 5. Thank you, everyone.